In this final block, we're going to talk about proof, showing properties of programs by doing mathematical style proof that they have these properties rather than testing or property-based testing or whatever. This gives us complete certainty of the behavior of programs over all their inputs potentially. If you remember, we foregrounded this in week 5 when we talked about the two ways that we might rotate a picture when we had the ASCII representation of those pictures. We could either reverse all the lines and then reverse the list of lines, or reverse the list of lines and then reverse all of them. So we claim, and perhaps it's visually obvious if you look at the diagram there, that we can prove this general property, that if we reverse map of fx's, that's the same as reversing x's and then mapping f along the list. It doesn't matter whether we do the map before or after the reverse, or conversely, it doesn't matter whether we do the reverse before or after the map. And in order to do that, to prove that for all x's, or for all finite x's, we use what's called induction over lists. So let's talk about what that means. What do we mean when we say induction? Well, what do we mean when we say recursion over lists? We have a template for defining a function foo. If you remember, this is the template from earlier in the course. To define the function foo over all lists, we say foo of the empty list is, and give a value for that, and we define foo of x colon x's, x cons x's, in terms of foo of x's and x. So that's how we define a function that works over all lists, or at least all finite lists. How do we do a proof? Well, we do a proof in exactly the same way. You can think, if you like, that induction is defining proofs by recursion. So if we want a proof for all lists, we have to give a proof for the empty list, and then we give a proof for x colon x's using the proof for x's that we've already got. So in other words, making it sound a bit more mathematical, we say we prove for the empty list, and then we prove for the list x cons x's, assuming the proof for x's. And that gives us a proof for all finite lists. So there's a slight caveat here, and I will come back at the end of the block to talk about what I mean by finite lists. And just to let you in on it, I think we've seen already that there are infinite lists in Haskell because of lazy evaluation. And I'll talk a bit more about how we think about proofs for those at the end of the block.